It's kind of difficult. But if we have the change of the mass flow rate with length. Okay, next, what's your name? Jared? Trin? But if we have the change of mass flow rate, m dot is a mass flow rate, m dot g is a mass flow rate of gas. But you have change of mass flow rate of gas along the way.
Those lighter hydrocarbons are escaping the oil in that change.
Yeah, there's some oil come out of gas, right? When pressure drop, when we have more pressure drop, then some more gas coming out of oil phase. So we have more gas, so more gas mass. So there's a change of gas mass flow rate too. Because there are several changes, the calculation will be quite complicated, and then the iterative model is needed. We don't cover it. There are several ways to solve it. Maybe use Runge-Kutta framework or something. Just know the name. So we skip. Okay. Let's take a look at mechanistic model. Mechanistic model. Step number 1 of using model is find the flow pattern. After find the flow pattern, then we find the liquid hole. Then we calculate gravitational pressure loss, frictional pressure loss, and then total pressure loss. Notice that most of the time we just neglect the accelerational pressure loss, okay? Because it's difficult to do. It's not because it's not important, it's kind of difficult to account for that term. Let's take a look at flow pattern. I have 0 degree, okay? Prediction is a line, the dot is measurement, okay? dB is dispersed bubble, SS stratified smooth, SW stratified wavy, A annular flow, VSL vertical axis is liquid flow rate, VSG gas, superficial liquid velocity, superficial gas velocity. When I look at this, you can see that if I have low gas flow rate, low liquid flow rate, the most likely flow pattern is stratified smooth. Okay. If I increase more liquid, it can change to I, intermittent flow. Open symbol means elongated bubble flow. Closed symbol means slug flow. Okay. So if I have low gas flow rate, it is elongated bubble flow. If I want to change from elongated bubble flow to slug flow, I increase gas flow rate. So if I increase gas flow rate, it moves right side. Right? If I want this bubble flow, I need a lot more liquid flow rate. Okay. Most of the time, if I have high liquid flow rate, low gas flow rate, it becomes dispersed bubble flow, dB. Good? So now you should be familiar with this flow pattern map. If I give you the flow pattern map, and I ask you what is the flow pattern for VSL equal to something, VSG equal to something. Can you do it? Yes? Okay, next. Danny or Danny? Danny. VSL equal to 1, VSG equal to 1. What is your flow pattern for 1-inch pipe?
Intermittent flow.
Is it elongated bubble or slug flow?
Slug.
Slug flow. Very good. Okay, question. Okay. Legend of that? No, I didn't put it there. No, I didn't put it there. But the only thing that you need to know is on the intermittent flow, on the left side is elongated bubble. On the right side is slug flow. Just that. Okay, now let's take a look. What is the impact of diameter on flow pattern? Even have pipe diameter to be double from 1 inch to 2 inch. It looks just the same, isn't it? Is it? Look the same. Not much change. Maybe it's changed in minor thing, but the graph itself looks very similar. Okay. So, oh, look at this. theta equal to 0, I change to theta equal to 0.25. Increase just a little bit. You see what happened? Intermittent flow regime, expand a lot. So for slightly upward flow, the majority of the flow pattern is intermittent flow. Okay? You see the intermittent flow area expand quite a lot. Initially it's just that big, right? When a slightly upward flow, it expands very big, like that. See that? So flow pattern is very sensitive to inclination angle. Okay? When I make the pipe to be bigger, 2 inch and 1 inch, it looks similar. Maybe this portion is the different. Okay? 0.5 intermittent zone is largest. Okay? 1 degree intermittent zone is largest. 2 degree, same thing. 5 degree, same thing happen. So what happened is when I increase the angle, the stratified wave flow regime shrink, and eventually it's gone. 30 degree, there's no stratified. It's just slug flow. Okay? It's just gone. Increase to 50 degree, I have just this bubble flow, intermittent and annular flow. Nothing else. 70 degree. Oh, look at this. From 50 to 70, I have churn flow. Churn flow between intermittent and annular flow. Churn flow is dependent upon the length of the pipe. So if I have pipe that's long enough, at the very end, churn flow is gone. Okay? Churn flow is just the entrance flow pattern for slug flow. Okay. 80 degree, we have more area for the churn flow. 90 degree, we have churn flow. Oh, you see something different. B, you see B, intermittent flow, and I have B over there. Bubbly flow or bubble flow. We have one more flow pattern. Okay? So when I go from small pipe is 1 inch, to a bigger pipe, 2 inch. This whole part, I get kind of bubble flow instead of intermittent flow. This tells me that the experiment that is done in the small pipe cannot be directly upscaled to larger pipe. Got it? Because one flow pattern just pop out, right? So this means we cannot easily upscale it. Something that is done in small pipe, we cannot use a scale and try to upscale it into the big pipe. The flow pattern may not be the same. Okay? We may have bubble flow over there. 80, 85, 90 degree. So in conclusion, upward flow, most of the flow pattern that you will see is intermittent flow. Larger pipe has more chance to get bubble flow. Small pipe has more chance to not have bubble flow. You see, 1 inch doesn't have bubble flow, but larger pipe has bubble flow. What happens is, to have slug flow, we need a bullet shape, right? If the pipe is small enough, the bullet shape stay there. We can have a slow moving Taylor bubble. But if the pipe is big enough, that Taylor bubble doesn't occupy the whole space. So it doesn't form a complete Taylor bubble and it doesn't form a slug flow. Okay? Just so you know that. The change in the pipe size, when the pipe becomes bigger, we may have different flow pattern. Bubble flow pop up. And all this is for water and air. Okay. Air water test. If we have oil, like the viscosity between 1 and 10, it may look just similar to this. But if you have emulsion, okay, like 30 centipoise 100 centipoise, the flow pattern may be different than this. Okay? Will probably be different than this. Now let's compare horizontal and the downward inclined flow. Downward inclined flow. So 0, we have stratified smooth, stratified wavy, intermittent flow, this bubble flow, annular flow. In the lab, okay, next corner black. Do you remember what happened in the lab? When I have downward flow, what kind of flow pattern that is very likely to see for downward flow? Stratified flow. Look at the stratified regime. SS, you see this? SW, stratified wavy, stay on top of stratified smooth. And total stratified area expand. And larger pipe is expand even more. Okay? This is just -1. A little bit down. -5, everything is like stratified wavy in this case. Larger pipe, we have some area for stratified smooth. -10, stratified wavy. Okay? It just formed the wave. -30, stratified wavy. We can have some intermittent regime shrink quite a lot, right? When we have downward flow, even 1 degree. So intermittent flow become smaller and smaller and smaller. -10, -30, okay. -50. Majority of the flow pattern is stratified wavy. Okay. -70. Oh, okay. Now there's something happened. You see, A become stay on top of stratified wavy. What is this about? Okay, next. What's your name? Austin, right? Okay, Austin. Annular flow. When it stay on top of that, why do we think we have annular flow like that? What is the annular flow for -70? Annular flow means gas stay in the middle, liquid stay around, right? For -70 is kind of falling film. Okay, falling film. -80, -90, everything become falling film. There's no more stratified flow. Everything become falling film. Okay. -80, we may have some stratified flow, but we have falling film too. Okay, annular flow. Have you seen falling film before, Austin? Yes, it is in the lab. The return line in the lab look like the falling film. Okay. So -90, completely downward flow. We have most of the time we have falling film. Sometimes we have intermittent flow. But if you look in the lab, intermittent flow, downward flow, the bullet shape still point up, right? It just look like this, but it's flowing down. The bullet shape, the tip of it is still pointing upward. Okay? Alright, you have seen flow pattern. Flow pattern map is dependent upon liquid and gas property. Most of the time is density, viscosity, interfacial tension. Okay? And also pipe diameter, length from the inlet. Okay? And it's very sensitive to angle. So this means if I give you prediction of a flow pattern map for water, and you want to use it for oil, you use it at your own risk. It's not one-to-one like that. Okay? If you want to use it for oil, you have to generate again. Okay? Buy the book. The book has a software to generate it very quick. Okay? So flow pattern is depend on diameter. I generated for 1 inch and 2 inch. Can I use it for 10 inch? Can I? No, I cannot. I cannot use it with confidence. However, I may use it because it's still better than don't do anything. So think about this. I have 0 degree. Okay, VSI equal to 1, VSC equal to 1. And I have like intermittent flow, 0 degree. So if I do it for 3-inch pipe, I don't have the data, and if I don't simulate it, can I say that it's going to be intermittent flow? Yes, I can guess, and most likely it will be correct. Okay, I think. To know it for sure, I have to generate it. But this flow pattern map, you can kind of use it for extrapolation a little bit. Okay, it's better than just random guess. All right, how do we do the flow pattern with other pipe diameter or other viscosity? To do flow pattern, we need to use a chart. Okay, this method we call Taitel-Dukler pseudo-stratified model. We assume that it is stratified flow first. Once we assume that it is stratified flow, then we can check if it is stable enough to be in stratified region or not. Okay. This model requires a chart. You see this chart? Okay. Step number 1, assume that the flow is stratified. So this model is just for horizontal and near horizontal flow. Okay. Step number 1, calculate x and y. Okay. This formula gives you x squared. Take the square root after get x squared. Why do we have to say this? Because many students didn't take the square root and it's wrong. Okay. X squared is defined as frictional pressure loss based on superficial liquid velocity dPdL sub FSL and dPdL sub FSG. Okay. So it's a ratio. If x squared is high, this means we have a lot of liquid. If x squared is a lot less than 1, this means the frictional pressure loss comes from mostly gas. Okay, so x squared, I think they call Lockhart-Martinelli parameter. It gives us some understanding on friction from liquid or from gas, which one is more. So minus dPdL, you see this formula, the one over here, 4Cl something 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 something. What is this one? Okay, next. What's your name? Sterling. What is Cl multiplied by that thing? What is this part? Friction factor. Okay, it's just a Blasius type friction factor. Blasius type friction factor is I think it's this formula: C multiplied by Reynolds number to the power of n. N equal to 0.2 for turbulent, and C equal to 0.046 for turbulent. So this is fanning friction factor. It is just fanning friction factor. And when I multiply 4 divided by 2, it's like 2F2, right? 4 over 2 is 2, right? 2F rho V squared over D. So on the top is frictional pressure loss based on superficial liquid velocity. My point is we can calculate the top part and the bottom part right up front. Why do I say that? Look at VSL. I can get VSL right away. I don't need to know liquid flow up, right? I need to know just actual flow rate in the pipe. And I need to know what is the pipe diameter, just that. Then I can get VSL. Formula for VSL is what, Sterling? What is the formula for VSL?
Flow rate.
Flow rate divided by
Area.
cross-section area. That's VSL. Rho L, mu L, those things is known, just fluid property. So I get C or this friction factor, right? Rho L VSL squared. So the top part I can calculate it. And the bottom part is just for gas based on VSG and mu G. Okay? Then I get x squared, I take the square root. The next one is the dimensionless gravitational term. Y, capital Y. Capital Y is 0 for horizontal flow, more than 0 for upward flow, less than 0 for downward flow. I have theta rho, G sine theta divided by minus dPdL sub Fg. Okay, 4 And this is fan friction factor, rho v squared over 2d, or 2f over v squared over d. That's capital Y. It's just put the number in the calculator and get the right value. Okay, next, Sterling, what's your name? Caleb. What's the unit? What is the unit you want to use when I write it like this?
SI.
SI. If you ever use pound force per square feet or something, you will need G sub C. Okay? So if you do pound per cubic feet and you do like feet per second or something, you probably need G sub C. But this formula is given in meter. Okay? Meter per second, kilogram or something. Okay? Use SI. So once I know X, I know Y. So let's say X equal to 10 to the power of 0, which is 1. And Y equal to 0. Okay. This line is Y. Y equal to 0 is this line. Okay, that's the Y equal to 0. I'm sorry, but you know it's middle line. Then I read the left hand side. Then I get the value of HL tilde, HLOD. HL is liquid height. Okay, got it? HLOD, liquid height. This is step 2. Just use the chart. Not that difficult, right? Is it? No. Okay. For x equal to 1 and y equal to 0, it's easy. Okay. What if my x equal to 0.01 or 10 to the power minus 2 and my y equal to 4, slightly upward. Capital Y equal to 4, I have two lines. That line and that line. Oh, actually, not two lines. So, I have three answers. Okay. I have the cross point can be that, or that. Is it that one? Could be that. So I have kind of three answers. What do you do? Use the smallest one. Okay. When you have three answers. So more than 6, I don't think we have problem. So if I have x equal to 0.1 and y equal to 5, I just have one answer, right? So next thing, we have to worry about dashed line and solid line. It's almost the same, but it's not. Dashed line is the case where liquid is turbulent and gas laminar. Okay. Solid line is for liquid turbulent and gas turbulent. Okay. That's the solid line. How do I know that liquid is turbulent and gas is turbulent or laminar? I don't know any of that until I finish my calculation, but the quick way of looking at it, I can look at superficial Reynolds number. Okay, I can look at superficial Reynolds number. Rho VD over mu. That value, if it is more than 2100, I can assume for now that it is turbulent flow. If it is less than 2100, I can say, okay, laminar flow. Alright? But superficial Reynolds number doesn't tell if the liquid phase is laminar or turbulent. I need the actual. To get the actual Reynolds number, I need a liquid hole up, but I don't have it yet. Okay? But just estimate, you may use that one. Okay? So that you know whether you use dashed line or solid line. So the stratified model for the flow pattern, we assume everything is stratified first. Then we get liquid height, dimensionless liquid height. Okay, I go do this and I read the value. So this means maybe 0.525 or something over there. Okay, I get the liquid height. So this means if it is stratified flow, the height will be 0.525. the dimensionless height will be maybe about half of the path diameter. Good. So after I know HL over D, next step is to use another graph. So this graph is for angle between -10 and 10 degree. I have A, B, C, D, several transition boundary. Okay. The order is A, B, C, D. Okay, that's the order. I will look at transition A first. Then I will look at transition B, and then C, and then D. Okay? Is it easy now? So I use that chart to get HL over D. Then I come back, use this chart. And I look at the transition A. Okay? Transition A will tell me if it is stratified or not. Okay. If it is stratified flow, transition C will tell me if it is stratified wavy or stratified smooth. Okay. And this chart has multiple variables. Let's go through it one by one. Another chart is just for 0 degree. Okay. And this analog flow chart, we will cover that. Okay. Step by step ABCD means what? Transition A use F versus H tilde. Okay, that is for transition A. Let's go back. F is where? That is F. Okay, that is H tilde for transition A. How do I calculate F? There's a formula. F equal to blah 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 blah. That is the value of F. Okay? So let's say I calculate F. And my F is 0.1. Okay? HL over D is 0.4. So when I am at that point, I look at transition A. Karen, do I have stratified flow or I don't have stratified flow? Or you cannot tell because I didn't tell you yet. Above the line will be non-stratified. Below the line will be stratified. Do you have stratified flow? Yes, right? Yes, because it's below the transition A. So if it is stratified flow, we will check transition C. If it is stratified smooth or stratified wavy. To check transition C, we have to use K versus HL tilde. How do I calculate K? K is K square is F square superficial random number of liquid phase. I take the square root of that, then I get K value. Okay? It can be calculated. It just takes some time to put in the calculator, just that. So I calculate K. So if my K is this much, or 0.02. At the corner is 0.001, right? That line is 0.002. And my HL tilde is 0.4. So I'm in that region. In that region, I have stratified smooth. Okay? If my, I have to look K value from this side. It's not the same, I'm sorry. I have to look K value and the scale is not the same. Okay, let's say my K value is 2 and that is log scale, okay. If K value is 2, I have certified smooth. If K value is 1, then I have certified wavy. Got it? Okay. What if I check transition A and it's not stratified? Then I have to check transition B. Transition B is HL tilde versus X. Transition B is to check if it is analog flow or not. Okay. So let's say I check transition A already, and my point is over here. When I look at F and HL tilde, I get that. Oh no. I have to get that point. So if my point is over there, this means it's not stratified flow, right? So when I plot F versus H altitude, if my point is over there, this means it's not stratified flow. Then I check transition B based on H altitude. So that point is annular flow. Done. Okay. What if it is not annular flow? Hey, let's say I check my point, transition A. I plot F versus HL over D. And my point stay over there. That's my point. Does it mean that I have intermittent flow? Not yet. I cannot make that conclusion yet. So when I plot F versus H altitude, even though my point over there is over there, then I have to check transition B. Hey, I am outside annular flow region, so it's not annular flow. Next, I have to check transition D to check if it is this bubble flow or not. To check transition D, I use different pair. Transition D is T versus H altitude. So when I look at my T, I have to calculate my T value. T value is this formula. It's not the same as F. So when I calculate T value, then if my value is inside the dispersed bubble flow region, then I'm in this bubble flow. If my T value is outside, then I'm in intermittent flow. Good? So the last one is, I think they call it transition K. Need to be checked for downward flow. Transition K is something a little bit more in depth, so we just neglect it for now. For basically for downward flow, we can have stratified wavy too. The mechanism to make stratified wavy is we have more mechanism than the mechanism we use in transition C. After that, I still have one more minute, okay? This is 12:19. So the formula of this will be given. Your job will be just have to do the calculation. Oh, transition K is not too difficult. Transition K is to calculate Froude number. Froude number use actual velocity over square root of GHL. So if Froude number is more than 1.5 and it is double flow, then we have stratified wavy. Okay, that's Froude number. All this formula has to be given for you to be able to do anything. Thank you for coming. See you next time. Bye bye. For those who need to check the grade, please follow me.